What exactly is a vector? It depends on who you ask. First, look at the physical world. To a physicist, a vector is simply an arrow in space, defined purely by its length and direction. It doesn't matter where you put it. If the push is the same, the vector is the same. But now, let's lock it into the grid. Enter the mathematician. Suddenly, that arrow is tethered to an origin. It becomes a set of coordinates, a bridge between geometry and algebra that allows us to define abstract operations like addition. Finally, strip away the visual entirely. To a computer scientist, a vector morphs into something cleaner, an ordered list of data. It is no longer just an arrow in 3D space. It is a static array, capable of scaling to thousands of dimensions, representing anything from a user's age to a pixel's color. 3 distinct perspectives, 1 universal concept. Let's take a closer look at how vectors behave in a 3-dimensional space. We begin with addition. The most intuitive way to visualize this is the tail-to-tip method. Watch as we draw our first vector and then place the start of the second vector exactly where the first one ends. The sum is simply the direct path connecting the origin to that final destination. Next, let's look at subtraction. This can be tricky, but it helps to think of it as just adding a negative. We take our second vector, flip its direction completely effectively making it negative, and then add it to the tip of our first vector to find the difference. Now, consider scalar multiplication. This operation is purely about magnitude. When we multiply a vector by a scalar, like 2, we aren't changing its direction at all. We are simply stretching the arrow, doubling its length in the exact same orientation. Finally, we can break any vector down into unit vectors. Think of these as the building blocks of the coordinate system. We can trace a path moving distance along the red x-axis, shifting across the green y-axis, and finally rising up the blue z-axis to reach our specific point in space. In standard mathematics, dividing one vector by another is undefined. However, in the world of computer graphics and homogeneous coordinates, we perform something called a perspective divide. Imagine a vector extending through 3D space, where the third axis represents a scaling factor. To normalize this vector and map it back to our viewing screen, we divide the entire vector by that W component. Visually, this slides the vector along its own path until it pierces the plane where W equals 1, locking the perspective correctly onto the 2D image plane. In ordinary vector spaces, we can add vectors and scale them, but division is not defined. To understand what vector division really means, we move into homogeneous space, where each point is represented not just by a position, but by a direction and a scale. All points along a ray from the origin represent the same location, differing only by scale. To recover the familiar world, we introduce a reference plane where W equals 1 and slide the point along its ray until it intersects this plane. This intersection is the true point. Dividing by W is not an algebraic operation. It is a geometric normalization. The scale disappears, leaving only position. When we project back to 2 dimensions, we recover the familiar coordinates. Vector division, in the end, is not really division at all, but the act of intersecting a ray with a reference plane, letting geometry do the work. Next, we will define position here. We need 3 axes, x, y, and z. Consider this blue vector at coordinates 3, 4, 3. To find its magnitude, or total length, we use the 3D distance formula. By squaring and adding the components, we calculate that this specific arrow is approximately 5.8 units long. But sometimes, we only care about direction, not length. If we divide the vector by its own magnitude, we get the unit vector. Notice how it shrinks? This red arrow points the exact same way, but now has a length of exactly 1. Finally, how is it oriented? Direction cosines measure the precise angles formed between the vector and the x, y, and z-axes. Let's break down span and basis. Start with a single green vector. Its span is simply a line, infinite scaling in one direction. Now introduce a second independent vector. By combining them, we unlock the entire plane. Notice how the grid transforms. We can now reach any point on the screen. This is a valid basis. But there is a trap. If our second vector lines up with the first, it is redundant. The entire grid collapses back into a single line. This is linear dependence. We are stuck in 1D, failing to span the full 2D space. Let's visualize what a basis actually means. We start with our standard coordinate system, defined by two perpendicular unit vectors, I hat and j hat. They are independent, and together they span the entire 2D plane. But a basis doesn't have to be rigid. Let's morph the grid using two new vectors, v and w. Notice how the coordinate system skews into parallelograms? Even though the angles change, the grid still covers every single point in space. This is a valid basis. However, watch what happens if our second vector lines up with the first. Because they point in the same direction, they are redundant. The entire grid collapses into a single line. We have lost a dimension. This is linear dependence, and it fails to form a basis. Let's visualize span and basis in true 3D space. We start with a single green vector. By scaling it infinitely forward and backward, its span creates a single line cutting through the void. Now, let's introduce a second vector. Together, they weave a flat 2D sheet, a plane. Notice how every possible linear combination of these two is trapped forever on this thin blue surface. To span the full 3D universe, we need a third vector that breaks the pattern. One that points off the sheet. This independent set is what we call a basis. But watch out. If that third vector falls flat and lies on the plane, it creates a trap. It adds no new dimension. It is linearly dependent, and our span collapses back into 2D, failing to build a true 3D basis. Let's compare span versus basis side by side. On the left, we have span. Span is about coverage. In 1D, we can have 3, 4, or 100 vectors all lying on the same line. They span the line, yes, but it's redundant and messy. On the right, we have basis. A basis is about efficiency. To define that same line, a basis uses exactly one vector. No more, no less. In 2D, the span might use 3 vectors to cover the plane, creating redundancy. A basis uses exactly 2 independent vectors to create a perfect grid. Span is the pile of building materials. Basis is the blueprint. Next, we try to understand coplanar vectors. Don't just look at the arrows. Look for the volume. Any two vectors naturally create a flat sheet, a 2D plane. When you introduce a third vector, the critical test is whether it sticks out from that sheet or lies flat against it. If the third vector points even slightly up or down, the 3 arrows together define a 3D box with actual volume. But if that third vector collapses onto the sheet, the height of that box becomes 0, and the volume vanishes completely. That is the definition of coplanar, when 3 vectors are so dependent on each other that they cannot build a volume, trapping them forever on the same 2D plane.